So today we will be discussing about the subroutine, the later part of the subroutine. Till now, we have seen that the subroutine uh, can be used uh, for making the program small and into the module. Suppose a big problem is given, which can be solved into the modules. So why not to break the problems into the modules, and different modules should be developed in such a way that individual module can be made with the help of subroutine. So bigger problem can be break into the small programs. And later on, all these sub-programs will be joined together. Now, till now, whatever subroutine instructions we have used, such as call and the return instruction, these call and the return instruction was unconditional call and the return instruction. But besides that, we also have conditional call and the return instructions. And another kind of the instructions which comes under the category of subroutine is the restart instruction. So besides call and the return instruction, we have 8 different types of restart instructions, which is actually the 8 different subroutines or the routines has been written for the different purposes. And these instructions are known as RST0, RST1, RST2, RST3, like that. So we have 8 RST instructions. So these RST instructions are single byte, and actually they are call instructions whose purpose is to transfer the execution of the program to a certain specific memory location where a routine is already written by, and it is being provided by the manufacturer of the microprocessor. So as far as the execution of the restart instruction is concerned, it is executed in a very similar fashion as the call instruction is being executed. So what happens when the RST instruction is executed? The microprocessor is going to store the content of the program counter. Now, what is the content of the program counter? It is the address of the next instruction to be executed. So before it is going to leave from the main program where the RST instruction is written to a subroutine, which is specifically written for the different RST instructions, it is going to store the content of the program counter, because while returning from the restart subroutine, it has to come back to the main program. So what it does, first of all, it will store the next address of the next instruction, that is the content of the program counter, on the top of the stack. And then it transfers the program to the restart location. Now, these instructions are generally used for the interrupt purposes, just to provide the services to those devices who has interrupted. And the other details we will be discussing later on when we will be discussing the interrupts in 8085. So what are the different RST instructions? One is RST0, whose address is 000, means it starts from page number 0 and at the location at the register number 00. So RST0 is actually call 0000. RST1 is again an instruction, which is a single byte instruction and is similar to call 0008. Now at 0000, there is a certain subroutine, there is a certain subprogram which is already written. So whenever RST0 is written, the program which is written from 0000 onwards, whatever is written, it will be executed. And then after the execution of that subroutine, which is written at 0000 memory location, after executing that, it will return back to the main program. So individual RST instruction have its own addresses. RST0 starts from 0000, RST1 starts from 0008, RST2 starts from 0010, and so on. Similarly, we have 8 RST instructions from RST0 to RST7. Now, besides this RST instruction, we have some conditional call in the return instruction. Conditional call in the instructions are such instructions uh, in which, until unless the condition is not satisfied, it will not move to the rest of the places. But in case of the previous call and the return instruction, it was unconditional instruction because it has to jump into that memory location which is written along with the call instruction. So in the conditional call instruction, the instruction may be checking the carry flag, it may be checking the parity flag, it may be checking the zero flag, it may be checking the sign flag. And depending upon the condition is satisfied, then only the subroutine will be executed. Otherwise, the subroutine will not be executed. So these conditional instructions are depending upon the 4 data condition, that is the flag condition, that is the carry flag, zero flag, sign flag, and the parity flag. And the conditions are being tested by checking the respective flags by the microprocessor. In case the conditional instruction, the program is transferred to the particular subprogram or the subroutine if the condition is satisfied. If the condition is not satisfied, that call instruction will not call that subroutine. So what we'll be doing while using this conditional call instruction, until unless the condition is not satisfied, the subprogram will not be executed and it will be executing the main program in a sequence. So So first one is call on carry. Call on carry means if the carry flag is set, then the subroutine will be executed by the given address. Now, the conditional call instruction is also having the format CC 16-bit address, CNC 16-bit address, CZ 16-bit address, and these address are the address of the memory location where the subroutine is written. So CC stands for call on subroutine, CNC call on no carry, CC is call on carry, CNC call on no carry, CZ call on zero. When it will call the subroutine if the zero flag is set. Similarly, call on no zero. If zero flag is not set, then subroutine will be executed. And these subroutine will be, these instructions are followed by 16-bit address, which represents the address of the memory where the subroutine is written. Similarly, call on minus means if the number is negative, if the sign flag is set, which means number is negative. So if the number is negative, then we will be using CM. So if the number is negative, then only it will jump to the 16-bit address and execute the subroutine. Similarly, CP stands for call on plus. If the positive number, if the result is positive number, it will check the parity flag. So it will check the sign flag. If the sign flag is zero, then it will call the subroutine and subroutine will be executed. Similarly, we have CPE. CPE stands for call on parity even. Call on even parity. And the last one is call on odd parity. So what it actually means that depending upon the condition of the flag, you can use the call instructions CC, CNC, CZ. If it is set, then only it will, until unless the condition is not satisfied, it will not jump to the subprogram, it will not execute the subprogram, and it will continue with the main program. But if the condition is met, a condition is satisfied, then only it will jump. It will go to the subroutine and execute it. Similarly, we have conditional return instructions also. Before that, we have studied return instruction as RET, but that instruction was the unconditional. It has to come back to the main program from the subprogram. But we have certain conditional return instructions also. The first one is RC. RC stands for return on carry. If the carry flag is set, then return. If the carry flag is not set, then return. RZ stands for if zero flag is set, then return. RNZ stands for if the zero flag is not set, then return. The return on minus, if the number is negative, then return. If the number is positive, means the sign flag is zero, then return. Return on even parity. If the parity bit is 1, then it will return. If the odd parity, if odd parity bit is 0, then it returns. So similarly, we have 8 different conditional call instructions, and similarly, we have 8 similar return instructions. Of course, all the conditional call instruction is of 3 byte, and all the conditional return instruction is of single byte. Similarly, similar to the unconditional call in the return instructions. Now we have some advanced subroutine concept, which is related with the nesting. Nesting of the loop you have already studied. Loop within the loop is called nesting of the loop. Similarly, it is also possible to call 2 subroutine within the one program. But if the subroutine are being called, either it should be independent, it should be separately placed, or if it is possible, it may be possible that a subroutine may be calling another subroutine. So if a subroutine is calling another subroutine, that is called nesting of the subroutine. Means subroutine within the subroutine is called nesting. So the process is called nesting. So this process is limited only by the number of available stack locations. When a subroutine is going to call another subroutine, all the return addresses are stored on the stack, and nesting can be illustrated in this way. Now, this is the illustration which will be showing how the nesting of the subroutine can be done. At 2050 in the main program, we are calling a subroutine which is placed at 2090. So what it will happen when this condition, when this instruction is executed, it will jump to 2090. So whenever it is executing the content of the instructions which is available at 2090 onwards, it is again going to found another subroutine that is called 20C2. So when this is being executed, so it means it has to go 20C2. So instead of executing the next, it will first execute the 20C2. And when this 20C2 onwards it is being executed, it will return. So when it will return to the place where the subroutine was placed. जहां से सबरूटीन कॉल किया गया था, रिटर्न इंस्ट्रक्शन वहीं पे जाकर के प्रोग्राम को बैक करेगा. And then when this subroutine is executed and this return instruction is executed, it will come back to the main program. So when a subroutine is being within a subroutine, we are using subroutine. So when the second subroutine is being executed, it will return to the first subroutine. And when the first subroutine is executed and it is going to return, it will return to the main program. So this kind of process is called nesting of the subroutine, and this is possible. Even though we can use a subroutine within the subroutine over here. So whenever this is being executed, it will jump to certain memory location which is defined within the call instruction. And whenever it has to return, it will return to this subroutine. When this subroutine will return, it will return to this subroutine. When this subroutine is going to return, it will return to the main program. So in this way, the nesting of the subroutine is being done. Now, it is also possible that for a subroutine, we have many return instructions which are available. We can use multiple ending subroutines. Now, this is going to illustrate, this figure is going to illustrate three possible ending of one call instruction. The subroutine has two conditional return instruction and one unconditional return instruction. This is possible. So at 2500, return 0 is written. It means before these, when the instructions are executed and 0 flag is set, then it will return. It will not execute the rest of the call. But if 0 flag is not set, it will execute the later part and it will check whether the carry flag is set or not. If the carry flag is set, then it will return. But if the carry flag is not set, it will not return and it will come. And when the return instruction is executed, it has to definitely return to the main program. So until unless the 0 flag is not set, when the 0 flag is set, it will return. When the carry flag is set, then it will return. If the ultimately, if both are not going to be satisfied, then finally it has to return by the return instruction. So with this, we are able to so let us now compare the instructions, which is call in the subroutine. It means the instructions which are used for call and return for the subroutine as well as the stack operations. Now, whenever we are going to compare the subroutine as well as the stack operation, of course, whenever we were using subroutine, call and return instructions are used. Whenever we were using stack operations, push and pop operations are being used. It means two different instructions are used for different purposes. If we have to use subroutine, we will be using call and return instruction. If we have to use stack, then we have to use the push and the pop instruction. So let us go and see what happens with whenever we are using call. So we are going to compare these two instructions. When the call instruction is executed, microprocessor automatically stores the 16-bit address of the next instruction onto the stack. No need to put a separate instruction for loading the content of the program counter into the stack. It is the call instruction which automatically does it the same. So when the call instruction is executed, microprocessor automatically stores the 16-bit address of the next instruction on the stack. But while using push and pop, push instructions are used to save the content of the register pair onto the stack. Second one is when the call instruction is executed, the stack pointer register is automatically decremented by 2. And when push instruction is executed, stack pointer register is decremented by 2 automatically. So we have not to use any separate instruction to decrement the value of the stack pointer. It is the duty of the instruction itself to do this. Third one is the return instruction transfers the content of the stack top location. The return instruction transfers the content of the top of the 2 locations of the stack to the program counter. It means while using call and return instructions, it means while using the call and the return instructions, since we are doing some operations related with the stack, but we have not to.
Sir.
So return instruction transfers the content of the top of the 2 stack into the return instruction transfers the content of the top of the 2 stack into the program counter. Of course, whenever we are using the stack operations, we have to use the pop instruction to transfer the content of the top of the two location into the specified register. But call and return instructions are those instructions in which the pop and push operation is already inbuilt. Because push on instructions are used to store the content of the register pair into the stack, and pop operation is used to take back the content of the memory back to the register pair. So in case of a call, while using call and return instruction, have not to use separate instruction as push and pop. It is already inbuilt in that. So whenever we are using call and return instructions, there is no need to use push and pop operation because it is being done automatically. While using call and the return instruction, it is not necessary to use push and pop because it is already inbuilt in the call and return. So it is the duty of the call instruction to store the content of the program counter into the stack, and it is the duty of the return instruction to call back, to take back the content of the top of the two stack into the program counter. When return instruction is executed, SP is already incremented by 2. When pop instruction is executed, SP's stack pointer is already incremented by 2. Besides this unconditional, there are certain conditional call in the return instructions which are available. But in case of stack operation, there are no conditional push and pop instructions. Only one single instruction, push and pop. It is not conditional, it is unconditional instructions. Now, let us discuss about a particular example that how to use the subroutine for how to use the stack operations. So that is why we are discussing some miscellaneous problems which are related with the stack and the subroutine. The first problem is write a program to add two hexadecimal number, that is 7A and 46, and store the sum at the memory location 8898, as well as the content of the flag register into 8897. So what simply we have to do, first of all, we have to clear the accumulator. We have to initialize the accumulator, and for that, we can use XRAA. The purpose of using XRAA is to initialize the accumulator, to reset the accumulator, as well as all the flag registers. Initialize the accumulator and reset all the flag registers. And then, since we have to add two numbers, so first number is copied into the accumulator. Second number is 46, it is copied into the B register. And we are going to add these two content by using add B instruction. So what it will do, it will add the content of B register with the content of A register, means 46 is added with 7A. And this, after the addition, the result will be stored in the accumulator. And if there is any carry or there is change in the result, that result will be reflected by change in the status of the flags. So what we have to do, we have to store these two, the accumulator which is having sum and the content of the flag register at the different memory location. So sum is to be stored at 8898 and flag register content has to be stored at 8897. So what we have done, we have initialized the stack pointer by 8899. So by initializing this, we are using push PSW. So by using push PSW, what we want to copy the content of accumulator as well as the flag register into the top of the two locations. So first of all, what happens when push instruction is executed? First of all, the stack pointer is decremented by 1. So when a stack pointer is decremented by 1, so it will become 8898. And the content of accumulator will be copied at 8898. Again, the stack pointer content is again decremented by 1, so that it will become 8897. And the content of the flag register, the 8-bit flag register, will be copied at 8897. And then program is going to halt. So this is the first program, first example. So this is the first example which will be showing you that how stack operations can be used to display the flag register content. The second one is the read the following program and answer the question. The program is written. Let us first understand the program. The first program which is written, the first line which is written is LXISP. It means we want to initialize stack pointer by 2100. Then we want to initialize BC pair register by 000. And then what we are doing, we are pushing the content of B. Whenever we are pushing the content of B, B means BC pair, means we want to store this 0000 in the stack. So while doing this, what will happen? First of all, the stack pointer content will be decremented by 1, and the content of higher order register, that is B, is stored at 20FF. And then again, stack pointer is decremented by 1, so that it will become 20FE, and the content of C register will be copied in that. And then what we want to pop PSW, means whatever is the stack top location. A stack top location is already having 0000. We want to pop into the PSW, means we want accumulator to be loaded with 00 and flag register to be 00. So first of all, what will happen? The pop PSW, when pop PSW is executed, the top of the stack location will be copied into the accumulator, the higher order register, and then the stack pointer is incremented by 1. Again, the top of the stack is incremented. Again, the copying operation is done from the stack top location to the flag register, and stack pointer is incremented by 1. And then again, we are copying 200B into the HL pair. And again, we are calling subroutine at 2064. And 2064, we have push H, push B, LXIB, DCXB, and the different instructions are written, and then it is going to return. And whenever it is going to return, it will be executing 200E, that is out 01. So in this way, this program will be doing, and we have to understand that how this, what are the different problems which we have to solve.